Hello everyone, today I'm going to introduce our work GP-SLAM Plus, which is a real-time LiDAR SLAM based on regionalized Gaussian process map reconstruction. As we know, simultaneous localization and mapping is one of the essential functions for autonomous robots. However, when working with low-cost and lightweight LiDAR sensor, the efficiency and the accuracy of SLAM suffer from sparsity and a large amount of point cloud. Thus, reliable registration method suitable for both state estimation and map building is needed. A wide range of existing literatures devote to build LiDAR SLAM. Many of them are based on an ICP method or its variants, such as SLOAN. Another option is to study the local properties of point cloud within subsections. Entity-based methods and server-based methods fall into these categories. There are also some works construct implicit surface like TSDF or IMLS. By contrast, we use GP as the model of environment, because GP is a continuous representation and can make inference with uncertainty in unexplored region. There are some work obtaining continuous occupancy grid map with Gaussian process. Some other work use spatial GP on terrain modeling or surface reconstruction. However, they mainly focus on mapping problems and do not include real-time state estimations and large-scale 3D mapping. The main contribution in this work are that we utilize spatial GP to recover local surfaces for sparse and noisy range data for SLAM. To do this, we overcome the computational complexity of GP to produce odometry and mapping in real time. We redesign the registration strategy to provide robust and efficient state estimation. We also employ a two-thread framework for large-scale tasks. The core idea of our method is the GP map reconstruction. We use spatial GP to reconstruct local surfaces from noisy range observations. The input of this process is the raw range data, and the output is the reconstruct map, which is ordered point with uncertainty. To establish different functional relationships locally and accelerate the reconstruction process, we divide the whole domain into separate voxels. Then determine the function relationship in each voxels as x equal Fy and Z, or Y equal Fx and Z, or Z equal Fx and Y, according to PCA. In detail, we assume three functions coexist in a cell generally to model complex 3D structures. However, we can ignore some direction when the local structure cannot provide a certain constraint. For example, in these figures, the black points are the raw data, and the colored point is the reconstruct results. Those predictions, remote from observations, are accompanied with larger uncertainties. As this set of raw data are drawn from a vertical wall, the function whose direction is Z will be neglected as the wall cannot provide a vertical constraint. To get more feasible access to data association and map updating, we extract discrete samples from the covered surface. They are evenly distributed and thus can be queried directly. In detail, given observations with Gaussian noise, we obtain the distribution of the predictions in preset locations by equation 1. Considering our predictions is mostly influenced by those observations close to them, the training process can be accelerated by principled downsample of the training points without much precision loss. One approach to complete this filtering process is utilizing the KD tree. However, as the searching targets in our application are evenly distributed, we can use a modified 2D voxel filter to approximate this process in linear time. With 2 frames of reconstruct result, we conduct a scan to map registration process iteratively to do the state estimation. As illustrated in these figures, a correspondence will be established between 2 samples from 2 frames when they satisfy those following conditions. First, they are located in the same or adjacent cell. Second, they share the same test locations. Finally, both the variance of the samples are below certain thresholds. Based on the idea that surfaces only offer observability in their directions, we design the error metric as the one-dimensional distance between predictions of samples rather than 3D Euclidean distance. Following the maximum likelihood estimation probabilistic scheme, we get the optimization problems. Then, the relative transform can be computed by this equation, where the variance can be seen as weight. This optimization problem is solved by nonlinear solver. Our registration is robust facing spare state as we focus on the local surface rather than row point. This figure is a demo that generalized ICP falls into run local minima with sparse states, while our methods align structure well. The error metric also significantly improved the coverage speed compared with our previous work, as shown in this figure. Map building is the other main part of the theme. We build the map incrementally, making use of the uncertainty and the convenient data association approach again. Correspondence are established in the same way, and a recursive list square update strategy is used. For large-scale text, we also design a 2-thread framework to decrease the drift. The refinement thread registers several frames of data. This framework is inspired by them. However, both threads in our systems use the scan to map strategy, so the core workflow can work independently. Then, we design experiments to evaluate our work from this different perspective, as listed in this table. First, to demonstrate the robustness of our methods when faced with sparse point clouds, we use a dataset collected by spanning to the LiDAR mounted on a micro area vehicles in a parking garage. The mapping result is shown in this video, in which the white points are eroded. Our map recovers the structure of the garage and the wall show field distortion. By the contrast, the GSP or surface-based methods produce distorted map even with graph optimization. Then we test the performance of the core workflow in our systems without IMU. Here we use alone as the benchmark. Firstly, we test the accuracy of state estimation with a hand-killed one-die VLP16 LiDARs at a walking speed. It is shown by the trajectory in this figure and the translation error interval 1. Both methods yield precise post-estimation. Then we test the quality of mapping results in an outdoor text with an MAV. As shown in this video, the map shows rich details. At the end of this text, there is a degenerate scenes for light slam as the MAV move up and down in front of a building. Our method also outputs more robust estimation. The reason is that the feature extraction strategy in A-long prone to lose more valid information than ours. Our maps show good alignment with the satellite image, with a maximal gap less than 1 meter. In the partial views in the right figures, the map of A-long contains multiple phenomena, but ours not. Our map is also sharper with lower mean map entropy. Here we also compare the efficiency of the scan-to-map registration process in both methods. Our core workflow completes both odometry and mapping in real time. Whereas the mapping thread in A-long have to drop dates, which will lead to accuracy loss. When break down the time consumption as least in Table 2, it can be seen that the GP map reconstruction is the main burden of GP-SLAM Plus. However, the complexity of this process is independent with the scale of the map. By contrast, A-long spend a lot of time in building and searching in KDG, which is quite expensive when the map is large. We also finish matching in linear time. Finally, we test the full system in a large-scale text with an IMU. The vehicle travel in a campus and the overall length of the trajectory is 2.1 kilometers. Here, we compare our methods with LEGO-LONG, which is an optimized version of LONG for ground application. It can be observed that our methods produce coherent maps and accumulate less drift, especially in terms of the elevation error. The map produced by the refinement thread show good alignment with the satellite image. This figure visualizes the drift of each method compared with the ground truth. Quantitatively, Table 3 lists the average translation error in XY plane and elevation. Our core workflow produces more precise estimations compared with the LEGO-LONG, and the refinement thread further enhances the performance. Last two main advantages of our methods are the robustness with the sparse point cloud and the efficiency. They are all derived from the GP map reconstructions and the proper registration strategy. It also opens the possibility to various kernel learning techniques for better performance, which is our future work. Thank you for listening.